What if a message was still traveling through space after nearly 50 years? Its signal travels across billions of kilometers through the darkness of space. This is humanity's most distant explorer. Welcome to Science Unlocked TV. Stay until the end to discover how Voyager 1 continues surviving at the very edge of interstellar space. Right now, a tiny spacecraft is farther from Earth than anything humanity has ever built. Its signal travels across billions of kilometers through the darkness of space. This is humanity's most distant explorer. Welcome to Science Unlocked TV. Stay until the end to discover how Voyager 1 continues surviving at the very edge of interstellar space. Right now, a tiny spacecraft is farther from Earth than anything humanity has ever built. Its signal travels across billions of kilometers through the darkness of space. Now, a tiny spacecraft is farther from Earth than anything humanity has ever built. Its signal travels across billions of kilometers through the darkness of space. This is humanity's most distant explorer. Welcome to Science Unlocked TV. Stay until the end to discover how Voyager 1 continues surviving at the very edge of interstellar space. Right now, a tiny spacecraft is farther from Earth than anything humanity has ever built. Right now, traveling at 17 kilometers per second, a small, silent machine is hurtling through the pitch-black vacuum of space. It is 14.5 billion miles from home. At that distance, light itself takes over 20 hours to make the trip. If engineers send a command today, they won't know if the spacecraft received it until almost 2 days later. It is operating in an environment no human-made object has ever encountered, pushing far past the boundaries of our solar system. And it is doing this with computer systems designed and built in the 1970s. Voyager 1 is no longer exploring the planets. It is exploring the space between the stars. And surviving out here requires a daily, desperate struggle to keep the aging hardware alive.
The most immediate threat is the freezing cold. The probe relies on a nuclear battery, a radioisotope thermoelectric generator, which loses about 4 watts of electrical output every single year as its plutonium continuously decays. This visualization represents the telemetry data from the probe's attitude control system.
In 2022, instead of returning a structured, ordered signal, the system suddenly started transmitting chaotic, randomly generated gibberish, even though the spacecraft appeared to be operating normally. The glitch was terrifying because it didn't trigger any onboard fault protection to put the spacecraft into a safe mode. Without valid telemetry, engineers were effectively flying blind, unable to verify if the probe's antenna was even pointing toward Earth. And the connection to Earth is heavily restricted for 11 months during a global pandemic. The only terrestrial antenna capable of transmitting the correct radio frequency to Voyager 2 had to be completely offline for major hardware upgrades. Managing these twin probes is a constant battle against physics and time, maintained entirely by a very thin, vulnerable thread of communication. To keep that communication line open and the antenna pointed at Earth, the engineering team has to take extreme risks. When Voyager 1's main thrusters started to degrade, they successfully fired up a backup set of trajectory correction thrusters that had sat completely untouched for 37 years. As the power supply shrinks, they also have to perform brutal triage. They are actively shutting down the heaters that keep the scientific instruments warm, sacrificing components one by one to conserve wattage. Yet, the hardware is remarkably resilient. Voyager 2's cosmic rays subsystem was exposed to temperatures dropping to -74°C, far colder than its tested limits, and it continued to return accurate data. These risky workarounds and desperate engineering hacks are the only reason we are receiving direct measurements from the interstellar medium today. For billions of miles, the sun's solar wind creates a massive protective bubble around our planet. The definitive, Boundary where that wind is stopped and overpowered by the pressure of interstellar space is called the heliopause. This graph plots solar wind particle density over time. As Voyager crossed the heliopause, detectors registered a steep drop to zero. Simultaneously, instruments recorded a sharp spike in galactic cosmic rays. The probe officially punched through our solar system's shield. The environment on the other side is entirely counterintuitive. The plasma in interstellar space is actually colder and significantly denser than the plasma inside our solar system. And the space itself rings with a distinct frequency. These same survival mode machines are the ones that previously discovered Io's active volcanoes and tracked the invisible escaping magnetic plasmoids around Uranus. Each transmission provides the first physical evidence of how our solar system's shield actually functions against the pressures of the interstellar idiom. But the grammatical reality is unforgiving. Sometime around the year 2025, or shortly after, the power levels will drop too low to sustain any of the remaining scientific instruments. The final sequence will be quiet. The systems will be shut down, one by one, to save energy, until eventually the radio goes silent, and Earth's final link to the spacecraft is lost forever. The loss of signal begins. Voyager's second mission, an infinite drift, where the probe transitions from an active instrument into a silent monument. Bolted to the spacecraft is a gold-plated copper desk. It carries a map of nearby pulsars, images, greetings, and dozens of languages, and the sounds of our planet.
Designed for whoever might one day find it, this physical time capsule ensures that even after the electronics freeze, Voyager will survive the vacuum as a permanent memory of humanity. The timeline of its journey outlasts history. In roughly 40,000 years, the silent shell will pass within 1.7 light-years of the star Gliese Vitus 445, billions of years. After that, it will drift through the Milky Way as the approaching Andromeda galaxy collides and merges with our own. Trillions of years into the future, star formation will cease, and the last slow-burning red dwarfs will finally burn out, darkening the universe. This visualization demonstrates what theoretical physics suggests will happen in an era of proton decay. The very atomic matter composing the probe itself will slowly break apart and dissolve into lighter particles, before it dissolves. It carries the legacy of a species that once turned a camera backward.
Begun.
Long after we're gone, this tiny spacecraft may still carry humanity's story among the stars. If you enjoyed this journey, subscribe to Science Unlocked TV, where every episode unlocks another mystery of the universe.